All right, so in this course, we're going to be taking a look at very simple problems that deal with independent events and dependent events. However, it's really important to distinguish between the two. So please make sure you understand the difference between an independent event and a dependent event, as well as mutually exclusive events and non-mutually exclusive events. Remember that mutually exclusive events cannot occur at the same time, whereas non-mutually exclusive events can occur at the same time. You have encountered these concepts in grade 9, and this lesson is just about making sure that you remember those concepts and that you distinguish between all of the different terms that are important in probability. Two events are considered to be independent if the occurrence of each event does not affect the occurrence of the other. So if we look at this symbolically, and remember that symbols are very important in probability, if we look at the intersection of two events, the probability of the intersection of event A and B, if the events are independent, then that simply means that we take the product of the probability of event A occurring and the probability of event B occurring. This isn't limited to just two events. It can be taken to 3 or more events as long as they are all independent. So symbolically, that is how we express independent events. So if you have intersections of event A and B or intersections of event A and B and C, then you simply take the product of all 3 probabilities for all 3 events. Now, how do we translate this into a real life example? A coin is tossed and a die is rolled simultaneously. Determine the probability of getting ahead and a 3 without using a grid. Really, it's important that we understand this as that multiplication rule for independent events. The multiplication rule says that when we have and, we can know that we're going to be multiplying the two probabilities together. So in other words, I know that I'm finding the probability of getting ahead and a 3. That tells me that I'm going to apply the multiplication rule. What is the probability of getting ahead? It's 1/2. What is the probability of getting a 3? It is 1/6. The two events are independent. They do not affect each other in terms of their outcomes. So you end up getting 1/12. And that's how we do that without using a grid. Now remember that grids and tree diagrams and other visual displays are important in trying to understand certain probability questions. However, others can be solved quite simply by remembering these rules with multiplication. It just depends on you and what you're more comfortable with, what is the most efficient and time-saving method for you. Let's take a look at example 15. Poor Carl is not having much luck lately. His car will only start 80% of the time, and his motorbike will only start 60% of the time, independently of one another. Draw a tree diagram to illustrate the situation. Use the tree diagram to determine the chance that on the next attempt both will start, or Carl can only use his car. So pause this video and see if you can answer this question correctly. Well, let's start out with the tree diagram. So first of all, we know that his car will either start or it won't start. When we are faced with that fork in the road scenario, given two choices, either starting and not starting, then I know that a tree diagram might be very helpful in solving a probability question like this. Anytime you're trying to decide what method or technique to employ in solving probability questions, you really have to interpret the question correctly. I know that I have two choices. The car is either going to start or not start. Maybe it's a choice that I don't like, but it's still considered a choice in the realm of probability. So, hopefully, the car starts, and it has an 80% chance of starting. But maybe I'm left with a car that does not start, and I have to see if my motorbike starts. Otherwise, I'm going to have to make a decision about what other transportation to take. So I know that the probability of the car not starting is the remaining 20%. Remember, 0.8 plus 0.2 equals 1, and that makes sense because 1 represents 100%. Now, once the car starts, the motorbike will either start or not start. So either the motorbike will start or the motorbike will not start. Notice the symbolic notation that I'm using. Remember that M prime represents the complement of event M. You did go over this last year in MYP and in grade 9. Well, in grade 9, not necessarily in grade 10. So hopefully this is coming back to you and you are accessing that prior knowledge. So the motorbike will start 60% of the time. So maybe both will start and you will be able to make a decision between either riding a car or a motorbike because both will start. But maybe just the car will start, and in that case, if the motorbike doesn't start, well, we know that you were unlucky because you landed on that 40% of it not starting. Now, the same is true if the car doesn't start. Well, if the car doesn't start, your motorbike may still start, so you do still have a chance to get to work, and that's going to be 0.6, or it may not start, in which case it'll be 0.4. Okay, so now we're going to be taking a look at all of the different probabilities here. So what's the probability that the car will start and the motorbike will start? So that's that intersection. And remember, because the two events are independent events, independent of each other, you can just take the product of the first branch. So that first branch will be 0.8 times 0.6, and that's going to be equal to 0.48. Then you can take the product of the next branch. So that is going to be the car starting and the motorbike not starting. So that'll be 0.8 times 0.4, which will be equal to 0.32. So a 32% chance that you will be in that scenario, or Carl will be in that scenario. The third branch is going to be the probability that the car will not start, but the motorbike will start. So in this case, you're going to have 0.2 times 0.6, which is going to be equal to 0.12. And then the last branch is going to be that they both do not start, which is a very sad day for Carl. So the car doesn't start and the motorbike does not start. So you end up with 0.2 times 0.4, and that is going to be 0.08. So an 8% chance. So we're lucky, Carl is lucky, I should say, that it's not very likely that both will not start for him. Now that we have all of these probabilities calculated, we can actually take a look at what they want us to answer. The probability that both will start, well, we've already found that here with 0.48, and the probability that the car starts and the motorbike does not start, which is going to be 0.32, that second branch. Okay. Liam rolls a 6-sided die twice. Determine the probability that exactly 1 4 is rolled. So go ahead and pause the video and think through this. Try it on your own. So here we are again, faced with a choice. What is the choice, you may ask? Either getting a 4 the first time or not. So we're going to define our events. Remember, it's really, really important that when you are deciding to call an event a certain letter, that you actually define the event. So let's call the events A and B. So let's say that the event A, sorry, I cannot speak today, represents that a 4 is rolled on the first roll. So 4 rolled first time. And let's say we have event B, where a 4 is rolled second time. 2 events. So either we roll a 4 the first time, or we don't, right? That's represented by that complement. So you've got probabilities that you need to set up. Well, you have a 1 out of 6 chance that you will roll a 4 the first time, and you have a 5 out of 6 chance of not rolling a 4 the first time. Now, let's say that you roll a 4 the first time. Maybe you're going to roll a 4 again on that second roll. So, you do, or you do not. And again, 1/6 and 5/6. Now, you didn't roll the die and get a 4 the first time, but maybe you get it the second time, or maybe you don't get it the second time and you just never rolled a 4 when you rolled the die twice. So you have a 1/6 chance here of getting it the second time and a 5/6 chance of not getting it. Now we get to answer this question, but before we do, let's translate this to symbolic language. So, what is this asking me symbolically? Pause the video and see if you can answer that. Well, to answer that question, we're going to have to look at what the question is asking specifically. Determine the probability that exactly 1/4 is rolled. Well, we've got a couple different scenarios in which that will happen. Either we roll a 4 the first time and we don't roll it the second time, or we don't roll a 4 the first time and we roll it the second time. Remember, or represents the addition rule, which is represented by an addition sign. So in other words, we want to know the probability of A intersect not B, or represented by a plus sign, the probability of not A intersect B. So, what does this mean? Well, that means multiplication. So we're going to take 1/6 times 5/6 plus, well, again, multiplication, 5/6 times 1/6. When you multiply these two parts of the expression and you simplify your fraction, in the end you get 5/18. That can be represented as a fraction, as a percent, or as a decimal. You should remember that your final answer should be simplified. Moving on to dependent events. What are dependent events? Well, let's take a look at an example. It says, suppose a hat contains 5 red and 3 blue tickets. One ticket is randomly chosen, its color is noted, and it is then put back aside and not put in the hat. A second ticket is then randomly selected. What is the chance that it is red? Well, now we're dealing with replacement versus non-replacement. This is obviously going to affect our probability when we draw again, because we are taking something out and we are not putting it back in. So that denominator is going to change upon the second draw. So if the first ticket was red, the probability that the second is red is equal to 4 out of 7. Now, the sample space originally includes 8 tickets. However, on the second draw, since you are not replacing and you got a red ticket the first time, you have 7 to choose from out of the 4 reds that remain. If the 4 tickets were blue, the probability that the second ticket is red, well, still that's out of 7 because you are not dealing with 8 possibilities because you're not replacing the blue ticket, and you have 5 reds to choose from instead of 4 because you still hadn't chosen a red the first time. The probability of the second ticket being red depends on what color the first ticket was. We therefore have dependent events. 2 or more events are dependent if the occurrence of one of the events does affect the occurrence of the other events. Events are dependent if they are not independent, which seems very obvious to us. It says, if A and B are dependent events, then the probability of the intersection of A and B is equal to the product of the probability of A and the probability of B, given that A has occurred. So the probability of A times the probability of B given that A has occurred. We are taking into account that A has occurred. If we are not replacing something, then that means we're dealing with dependent events because now your denominator has changed, right? So instead of 8, now you're dealing with 7 for that first example. So they reiterate what I just said in general when an experiment involves sampling. Without replacement, we have dependent events. With replacement, we have independent events. So sampling just means that we are, for example, drawing from a hat or drawing from an assembly line and either replacing the product or item or not replacing the product or item. Not all scenarios we study involve sampling, however, they may still involve dependent events. For example, the event that Bahal walks to school today is dependent on the event that it will rain today. So let's take a look at example 17 to ensure that we understand this concept. It says a box contains 4 red and 2 yellow tickets. 2 tickets are randomly selected from the box, one by one, without replacement. Find the probability that both are red and the probability that the first is red and the second is yellow. Without replacement means that the two events are dependent. So go ahead and try this on your own. The very first thing I'm going to do is I'm going to define my events. I'm going to call big R. That's going to be that the ticket is red, so red ticket. And yellow, Y is going to be yellow ticket. Spoke too soon there. So yellow ticket. Okay, so let's put part A in symbolic notation. So in other words, I want to find the probability that I get a red and then a red again. And more specifically, I'm going to take the product of the probability that I get a red with the probability that I get a red given that I got a red the first time. So the probability that I get a red is 4 out of 6. And then the probability that I get a red given that I got a red the first time is going to be 3 out of 5. And then you multiply those together, those two fractions, and you reduce and you get 2/5. Remember, you can always turn that into a percentage or leave it as a decimal. For the second question, the probability that the first is red and the second is yellow. So the first is red, well, there's 4 out of 6, and the second is yellow. Well, there's 2 out of 5 because I'm not replacing the red ticket, and I multiply those straight across, and I get a reduced answer of 4/15. Let's just take a look at the solution to this question together. So it says a hat contains 20 tickets numbered 1, 2, 3 through 20. If 3 hats are drawn from the hat without replacement, determine the probability that they are all prime numbers. So it says in each fraction, the numerator is the number of outcomes in the event. The denominator is the total number of possible outcomes. We already know this. So we've got this sample space. I find strangely that a lot of people forget what sample space is. A sample space is a list of all the possible outcomes. And remember that when we give a sample space, we do need to use those curly brackets to represent a set. So out of that sample space, 8 of the 20 numbers are primes. So we want to find the probability that we have 3 primes. In other words, what that is saying is that I draw once, I get a prime, I draw again, I get a prime, and I draw a third time and I get a prime, which is represented here symbolically. So if 8 of those 20 numbers are prime, well then you have 8 to start with, and then you've got 7, and then you've got 6, and simultaneously that denominator is going down by 1 because you're not replacing those tickets, and you get approximately 4.91%. All right, let's take a look at a more complex example. Example number 19. We've got 2 boxes, each containing 6 petunia plants. Box A contains 2 plants with purple flowers and 4 plants with white flowers. Box B contains 5 plants with purple flowers and 1 plant with white flowers. A box is selected by tossing a coin, and 1 plant is removed at random from it. Find the probability that the plant was taken from box A and has white flowers, and that the probability has purple flowers. Okay, so we've got some choices here. First of all, we have to figure out the best technique to employ to solve this question. You try it on your own. What are the choices that we have? Well, the choice isn't a coin toss. Although choosing box A and B is made through a coin toss, the choice isn't heads or tails, right? The choice is box A or box B. So we know that we have to choose between box A or box B, but we're going to choose either box A or box B through a coin toss, where you have a 1 in 2 chance of getting either a heads or a tails. So half and half, right? There's a 50% chance that you'll get box A and a 50% chance that you'll get box B because it's based on a coin toss. Once you make that decision, then you have to see if you either get a purple flower or a white flower. So if you choose box A, you can get purple flowers or white flowers. If you choose box B, you can get purple flowers or white flowers. So let's take a look. Box A contains 2 plants with purple flowers and 4 plants with white flowers. So 2 plants with purple flowers and 4 plants with white flowers. Well, that's 2 out of 6, which is equal to 1/3, which would make this 2/3, right? Because 2/3 and 1/3 is 3/3, which reduces to 1. Now, for the second box, box B, it says it contains 5 plants with purple flowers and 1 plant with white flowers. So 5 plants with purple flowers out of the 6, and therefore you get 1/6 remaining of white flowers for your probability. So find the probability that the plant was taken from box A and has white flowers. So the probability that it was taken from box A and has white flowers. Of course, I would define both of these somewhere when I'm problem solving. So let's go ahead and do that. A represents box A, and B represents box B, and W represents white flowers, and P represents purple flowers. So, to find this intersection, I am simply taking 1/2 times 4 out of 6. So 1/2 times 4 out of 6, which I reduced, right? So that's 1/2 times that 2/3, which is equal to 1/3. Okay, has purple flowers. Well, this is a little bit more complex because I can get purple flowers from box A or box B. So there's or again, and or means addition. So if I get box A, then I can get purple flowers, or if I get box B, I can also get purple flowers. So let's try this probability. So the probability that I choose from box A and I get purple flowers, or I choose box B and I get purple flowers. Either of those will get me purple flowers. I don't care which box. So 1/2 times 1/3 plus 1/2 times 5/6. Well, when you do this correctly and you reduce, you get 7/12. All right, let's take a look at the last one here. Ooh, what a doozy. So we're just gonna take a look at the solution. It says a bag contains 10 balls, 6 are black, 4 are white. 3 balls are drawn from the bag without replacement. Dependent events. Determine the probability that 1 black ball is drawn. So 3 balls are drawn from the bag without replacement. That should tell me alone that I'm dealing with a tree diagram, because I can either get a black the first time, or a black the second time, or a black the third time. So again, I've got that sort of fork in the road scenario where I get the black or I don't get the black. I get the black or I don't get the black. I get the black or I don't get the black. So you see here on this branch, black and then black and then black. And then black and then white and then white, or black and then white and then black. So one black ball, what are going to be all of those branches? So let's go ahead and just go through all of those different scenarios. So one black ball, well, you can either get one black ball by getting one black ball the first time and then getting 2 white balls, or you can get one white ball the first time and then you can get a black ball and then a white ball, or you can get a white ball the first time, a white ball the second time, and a black ball, right? So tree diagrams are important because they do allow you to better visualize all of these different scenarios, whereas if you were trying to do this on your own, you might have to think a minute or more than a minute and waste some crucial time here. So again, that's where the interpretation comes into play. Make sure that you're able to look at a problem and start thinking about the best strategy to tackle these problems. And I know this is revision for you, but I'm hoping that seeing this second time will allow you to say, hey, I've seen this before and I have enough exposure to finally be able to say to myself that I feel confident in finding a strategy to answer these questions. Okay, so your assignment today is a worksheet on this. If you are behind, which some of you are falling behind, please make sure you catch up. If you are struggling, please send me an email. If you need more time to catch up, please send me an email. Either way, I'd like to hear from you. Have a great day.